Hi, I'm Antonio Sala, and in this video we are going to compute statistical information, meaning covariance, of the derivatives of a stochastic process with given covariance function. Why do we want to compute these things? Well, because we can imagine, say, measuring positions of a moving particle and wishing to estimate, let's say, its speed, or wishing to use speed measurements to improve the position estimate. So in a generic case, we may wish to estimate partial derivatives of a stochastic process, or we may have observation of those partial derivatives. So suitably combining this information in statistical formula requires computing mean and covariance of these partial derivatives, which is the objective of this video. So we will consider a stochastic process, some function of some input arguments, n-dimensional fx, which is a random variable. So we know the covariance between those functions at different points x. If x were time, this would be the covariance of the process at different time instants. But okay, we are n-dimensional, so we are generic. Then, of course, with this covariance, we can write formulas for the conditional mean and variance of the process given observations of f at a given set of points, with best linear prediction formulas, and that's called Kriging, kernel regression, which are developed in other materials in this collection and also in many other places, Gaussian process regression. So, under some conditions, this stochastic process may be differentiable. Which are those conditions? Well, this is sort of the tricky part. This difference must converge with probability 1 to something, so rigorously stating what convergence of this actually means is the task of mathematicians. In here we'll not discuss the details of that existence, of the limit of this when h tends to 0, and we'll just think on, if I know the position and this is a mass, this must have a velocity, and then there must be some way to compute that velocity from, let's say, physical insight. But it's true that if I have a linear process, say an integrator, subject to white noise input, then this is not differentiable. So some caution is needed. We'll not discuss those issues and simply say that, if the formulas we are going to write below actually work and give a finite value, then it will be because, those derivatives exist. But a rigorous analysis would be needed from a mathematical point of view. But in here we are considering an engineering audience, so we understand what velocity of a randomly moving thing is. Then that thing is the thing we are going to compute here. So that thing will be the partial derivative of the stochastic process with respect to one of the input variables. In signal processing, x will be actually time, And of course, it will not be statistically independent of the originating process f, because, if I measure these positions, it's quite likely that the gradient has a very high correlation with the slope of the line joining these points or something like that. So the partial derivatives of a process and the process itself will not be statistically independent. At least that's what we intuitively expect in a general case. We may have several ways of computing statistical properties of the derivatives. We may have, say, an stochastic differential equation. In control engineering, we are used to name this thing time and this thing state, but it's a matter of notation. If x is multidimensional, then we'll have a stochastic partial differential equation. There may be solutions to them, matrix exponentials or things like that. That will be one way of doing these things. And in fact, it's kind of things done in Kalman filtering to estimate speeds, etc. Another option would be operating in frequency domain Laplace Fourier transform with, say, manipulations of the power spectral density of a process we are trying to differentiate. And a third way will be using the properties of the covariance function in the original coordinates, not transformed, Laplace, etc. And in fact, this third option is the one we are going to develop here, because it's kind of directly related to the definition of stochastic processes, some variables related with the covariance function, and because the manipulation of the covariance is the usual way of doing things in kernel regression, Kriging, etc. So this will be the main goal of this video. Of course, that does not preclude that in control or signal processing applications, we use other things like, Kalman filters, transfer functions, and results should be equivalent under some assumptions. But okay, in here we'll just use this covariance K to compute properties of the derivatives. So this will be the problem statements. We'll have a stochastic process f depending on n input arguments, and we wish compute the expected value of partial derivatives, the covariance between the original process and its partial derivatives, and the covariance between the partial derivatives at one point in one coordinate and a different point with respect to another coordinate, because this partial derivative will be another stochastic process with some statistical correlation with the originating one f. We'll start by the mean, which is the expected value of the gradient of the partial derivatives of my stochastic process. Well, we wish to compute this, the expectation of this limit, which is of course the partial derivative. Vector ek will be the unit vector in direction k, so this increment is taken in the direction of the kth coordinate. K may be any index from 1 to n. We'll first think in finite increments, forgetting momentarily about limits. So expectation is a linear operator, so constants can go out of the expectation, and then the expectation of the difference is the difference of the expectations. If we now take limits, then the expectation of the partial derivative is just the partial derivative of the expectation, because this is the partial derivative of the expectation, so we assume that mean value of the Gaussian process is a known function, f bar x. If I have some observations that f bar will be some function that interpolates the observations, and well, what we are saying is that the expected value of the velocity, the partial derivative with respect to this argument, is the derivative of this mean function. Good, we finished with the mean. Let us now consider variance and covariance of the partial derivatives. And again, by assumption, we need to obtain that only from the properties of the covariance function of the original f, k. If we assume that f and its derivatives are not independent, then our first goal would be computing the covariance between those two stochastic processes. And in fact, we may consider a point x and a point x prime in the derivative thing, because, well, the speed estimate at a point x prime will be correlated with the position estimates at another point x. So we'll do something similar to what we did with the mean. We'll use finite increments and then we'll take limits. So let us first consider the finite increment version of this partial derivative, which is this finite increment that, when I take limit of h to 0, will be the thing. ek is again the canonical vector in direction k. So, forgetting about limits, we'll take this expectation, and well, h can go out of the expectation, and if I compute these products, I'll get this product minus this thing when I multiply everything by f of x. And the expectation of this thing is, by definition, the covariance between x and x prime plus HAK. Okay, we should subtract the mean, but that would complicate the notation. So, as in many variance computations, quick and dirty calculations with zero mean just work, because kappa is actually the mean of f minus f bar at a point and f minus f bar at a different point. But okay, means cancel out. And I leave to you as an exercise to write the correct version with non-zero mean. But if you're familiar with variance computations, you know that, okay, when we say this, we are actually saying products of increments around the mean, but okay, things do work. But okay, the expectation of this product is this kappa, and of course, the expectation of this product is kappa of x dot by definition of kappa, abusing the notation because I did not put increments around the mean. Okay, but this is the finite increment formula, so when I take limits of h to 0, so that we get this thing gets converted to the covariance between f and its partial derivative, and this thing is the partial derivative of the covariance with respect to the kth coordinate of its second argument. This is the main result. And it's an easy exercise saying that if we had thought of the covariance of the derivative of x and f at x dot, we would have obtained the partial derivatives with respect to the first argument of the covariance function. So these are the formulas, the first derivatives of the covariance function, which give me the statistical covariance, a correlation between a stochastic process and its derivative. Now we'll pursue another goal, which is computing the covariance between the gradient itself. And in fact, if the process is multidimensional, I wish to compute the covariance between the partial derivative with respect to the ith coordinate at one point, x, and the partial derivative with respect to another coordinate, j, at a different point, x prime. So, again, let us first operate with finite increments, and then later on we'll take limits. This thing will be this partial derivative when we take limits when h1 tends to 0, and this thing will be this second partial derivative when we take limits when h2 tends to 0. So we'll first operate with this expression and we'll later on take the limits. So in here, the product of these two differences will give me 4 terms in the multiplications, these things, and of course h1, h2 dividing stuff can go out here, and I can just put a parenthesis here and change this sign, and that's what I did here. So we have this expression, and now I will insert h1 again inside the expectation. So h1 will divide this difference, and also h1 will divide this difference. Why? Because, well, I'm incrementing things by h1, so when I divide by h1, I'll get something which will hint me that there is a partial derivative over there. If I take expectations, then the expectation of this product is this kappa, the expectation of this product is this kappa, and likewise I have the expectation of this product and the expectation of this product. Good. Let us now take limits making h1 tend to 0. What is this thing? Well, we see that the second argument is constant. Now h2 is not infinitesimal, h2 is still a finite increment, so we can see that this thing, when h1 tends to 0, will tend to this partial derivative of the covariance function with respect to the ith direction in its first argument, xi, at this point x, because I have x and x plus an increment, and I am not taking derivatives with respect to the second argument, so the second argument goes here unmodified. Good. If I now look at this product, then again, second argument is unmodified, x prime, and this thing will be the partial derivative with respect, again, to the ith direction in the first argument. Here we have it. So now, when we take limits when h2 tends to 0, then we'll see that this is a function, okay, in which the second argument is incremented in the jth direction. We have x prime plus an increment and x prime here, so when we make that increment infinitesimal and divide by h2, we get the partial derivative of this thing with respect to the jth coordinate of the second argument. So we end up saying that the covariance between the partial derivatives, different directions, different points, is this cross derivative of the covariance function. So that is the main result of this last part of my video. So we will conclude. In this video, we have discussed that measuring velocities, partial derivatives, may be useful in some applications, or, well, measuring positions, I can estimate velocities. So the partial derivative of a stochastic process will be another stochastic process with some covariance, some statistical correlation with the originating process. Computing the expected value and the statistical properties, the covariance between partial derivatives and the original process, has been the objective of this video, and expected value of a derivative is just the deterministic, let's say, derivative of the mean, and then the covariance between the originating process and the derivative of it is the first derivative of the covariance, and the covariance of the partial derivatives themselves is obtained with the second cross derivative of the covariance function. So this is it. We finish with this our video. Thanks for watching.